In this episode, we're going to focus on two security outcomes that beginners sometimes overlook because they sound like operations problems, not security problems: availability and integrity. Availability is about keeping systems usable when legitimate people need them, and integrity is about keeping systems and data correct, trustworthy, and resistant to unauthorized change. In real environments, these two are tightly connected because a system that is up but returning corrupted data is not truly available in any meaningful sense. When we talk about engineering for availability and integrity, we are talking about designing systems that can handle growth, survive failures, recover from damage, and continue behaving predictably even under stress. That includes scaling to meet demand, being able to recover when things go wrong, maintaining persistence so you don't lose what matters, and using geography wisely so a single local event does not become a total outage. The key is to treat these as design requirements from the beginning rather than emergency fixes after the first major incident. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Scaling is the part of the story that deals with demand, and demand can come from good things and bad things at the same time. Good demand is when more users show up because the system is useful, and bad demand is when attackers or misbehaving clients flood the system with requests. The engineering challenge looks similar in both cases. Your system must handle more work without collapsing. But the security implication is different because malicious demand often targets your weak points and is designed to maximize cost or disruption. When you scale, you are building capacity and elasticity, meaning the ability to add more resources when load increases. That can improve availability by absorbing spikes, but it can also create new risk if scaling is uncontrolled and costs explode, or if newly added capacity is not configured consistently. A beginner-friendly way to think about scaling is that it is not just make it bigger, it is make it bigger without losing control, because losing control is how availability problems turn into security problems. There are two common scaling patterns that are worth understanding at a high level: scaling up and scaling out. Scaling up means making a single component stronger, like giving a server more resources. Scaling out means adding more instances of a component so the workload is spread across them. From a resilience and integrity perspective, scaling out often brings better fault tolerance, because losing one instance does not necessarily kill the service. But scaling out also increases complexity, because you now have to keep multiple instances consistent and you have to manage how they share data. Integrity can be threatened if different instances behave differently due to configuration drift or uneven updates. Availability can be threatened if your load distribution fails and all traffic piles onto one node. So the security-minded approach to scaling includes standardization, automated consistency checks, and careful control of changes, so growth does not create a sprawling, inconsistent environment that is hard to defend. Recoverability is the ability to restore normal service after something bad happens, and it is one of the most practical security capabilities you can build. Bad things include accidental deletion, software bugs, hardware failures, and deliberate attacks such as ransomware. Recoverability is not just about backups. Although backups are a major part of it, it is also about how fast you can detect a problem, how quickly you can roll back changes, and how confidently you can restore data without bringing back the same problem. For beginners, the key idea is that recovery is a planned process, not an emotional scramble. If your recovery plan exists only in someone's memory or in a document nobody tests, it will fail when it matters most. Recovery engineering includes practicing restores, verifying that backups are complete, and ensuring that restored systems are not immediately recompromised. A system that can recover quickly reduces attacker leverage, because extortion relies on making recovery seem impossible or too slow. Integrity and recoverability are closely linked because recovery is not just about having data, it is about having correct data. If an attacker can alter data silently, you may restore from backups and still end up with corrupted information if the backups contain the altered state. That means integrity engineering includes methods to detect unauthorized change, such as strong access controls, audit trails, and checks that reveal unexpected modification. It also includes separating duties so no single account can both change data and delete the evidence of change. In a beginner sense, integrity means you can answer the question, can we trust what we see? And recovery means you can answer the question, if we cannot trust it, can we roll back to a trustworthy version? These are security questions because many attacks are aimed at undermining trust, not just stealing data. A resilient design gives you ways to prove or restore trust under pressure. Persistence is about keeping critical states safe over time, even when components fail or are replaced. Many modern systems use temporary compute resources that can be destroyed and rebuilt quickly, which is great for scalability and rapid recovery. But that makes it even more important to define where the truth lives, meaning where the authoritative data is stored. If the truth is scattered across temporary components without a clear source of record, integrity suffers because no one can be sure which version is correct. Persistence is also about durability, meaning data survives crashes and outages, and about consistency, meaning updates happen in a controlled and predictable way. For beginners, an easy trap is to assume that because a system works in a normal day, the state must be safe. But resilience design asks what happens when the power goes out, when a region goes down, or when an attacker tries to erase evidence. Persistence planning answers those questions before you face them. A major integrity issue related to persistence is the problem of partial failure, where some parts of a system succeed and others fail. Imagine an operation that updates two records that must stay aligned, such as a payment record and an account balance. If one update succeeds and the other fails, the system can enter a confusing state that looks like fraud or corruption. Attackers sometimes exploit these edge cases by forcing timeouts, retry storms, or unusual sequences of requests that trigger inconsistent behavior. Resilient systems are designed to handle retries safely and to detect and reconcile inconsistent states. Even without deep technical detail, the lesson for SecurityX learners is that integrity is not just about stopping unauthorized users. It is also about designing systems so that failures and delays do not produce incorrect outcomes. When a system stays consistent under stress, it is harder to manipulate and easier to recover. Geography becomes part of availability and integrity when you consider that real-world events are not evenly distributed. Power failures, storms, construction accidents, regional network outages, and even human errors in a single location can take down a large portion of your infrastructure if everything is concentrated. Geographic resilience is the practice of spreading risk so that one localized event does not become a total outage. That might mean running services in multiple locations, maintaining copies of critical data in different places, and ensuring that failover paths are actually usable. Geography also matters for integrity because data replication across locations must be done carefully. If you copy corrupted data quickly to every location, you have replicated the problem instead of improving resilience. So geographic design is about balancing availability with controlled replication and about making sure that your backup location is truly independent enough to help when the primary location is in trouble. A beginner misconception is that having multiple locations automatically makes you resilient, but it can also introduce new failure modes. If the system fails over too easily, you can trigger unnecessary disruptions. If it fails over too slowly, users experience long outages. If the data is not consistent across locations, users may see different answers depending on where they connect, which is an integrity problem. And if your security controls are uneven, attackers may target the weaker location. That means geographic resilience requires disciplined standardization and consistent policy enforcement. It also requires testing, because failover that looks good on a diagram can break when real traffic, real dependencies, and real authentication flows are involved. Resilience is not theoretical. It must be proven in controlled exercises so you discover problems before attackers or outages do. Availability engineering also includes protecting against intentional disruption, which is where denial of service comes back into the picture. Even if you scale well for normal growth, an attacker may attempt to exhaust your resources, overwhelm your network, or abuse expensive features to drive costs up. The integrity angle here is that attackers sometimes mix disruption with deception, such as causing monitoring gaps during an outage or using noisy attacks to hide quieter intrusions. A resilient design includes layered defenses that absorb or filter abusive traffic and strong monitoring that stays reliable during high load. It also includes making sure that critical services degrade gracefully rather than collapsing entirely. Graceful degradation means that under pressure, the system prioritizes essential functions and reduces optional ones, so users can still do the most important tasks. This is a security win because it reduces the attacker's ability to turn pressure into full outage. Another critical topic is change, because many availability and integrity incidents are not caused by attackers at all, but by well-intentioned changes that had unintended consequences. A rushed update can introduce a bug that corrupts data. A configuration change can accidentally expose a service or break authentication. A dependency update can cause failures across multiple systems. Resilient engineering treats change as a controlled risk, which means using staging, incremental rollout, and fast rollback when things go wrong. It also means monitoring the right signal so you can detect problems quickly, like error rates, latency, and unusual patterns of data modification. The security lesson is that a stable change process protects you from both accidents and attackers, because attackers often exploit chaos and confusion. When you can deploy and roll back cleanly, you can also respond to vulnerabilities faster and with less fear of breaking everything. It helps to think about recoverability in time terms, because time is what attackers try to steal from you. How long does it take you to notice something is wrong? How long to stop the damage? And how long to restore normal operation? If it takes hours to detect corruption, the blast radius grows. If it takes days to restore, the business impact grows and attackers gain leverage. Resilience focuses on shortening these timelines through monitoring, automation, and practice. But integrity requires that you restore the right thing, not just anything. So you also need validation steps that confirm restored data is correct and systems behave normally. For beginners, a useful mental check is to imagine a worst day where a key database is corrupted and a service is down. If you cannot describe, in plain language, how you would restore service and verify correctness, then your design probably needs better recoverability planning. When we pull these threads together, you can see that availability and integrity are engineered through a set of reinforcing decisions rather than one magic control. Scaling provides the capacity to handle growth and absorb spikes, but it must be paired with consistency and control to avoid creating fragile complexity. Recoverability provides the ability to return to a trustworthy state after failure or attack, but it depends on backups, rollback capability, and practice. Persistence provides durable and consistent storage of critical truth, but it must be designed to survive failures and to prevent silent corruption. Geography provides independence from localized disasters, but it introduces replication and failover challenges that must be managed with care. If you treat these as security requirements, you build systems that are harder to disrupt and harder to manipulate. If you treat them as optional operational polish, you often discover their importance in the middle of an incident. The best way to summarize this for a SecurityX mindset is that availability and integrity are not accidental properties of a system. They are outcomes you design for and continuously maintain. You engineer scaling so the system can handle legitimate growth and resist abusive load without losing control. You engineer recoverability so you can restore service quickly and confidently, even in the face of destructive attacks. You engineer persistence so the system's truth survives failures and remains consistent, making it difficult for attackers to rewrite history. You engineer geography so a single regional event cannot erase your ability to operate, while still keeping data replication and failover safe and predictable. When you combine these decisions, you create resilience that is visible in calm operations and, more importantly, in calm recovery when something goes wrong. That calm is the real sign of good security engineering, because it means your system was designed to withstand the real world instead of hoping the real world would be gentle.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.